Let's look at the hydroboration of methylcyclopentene, and we're going to focus on not only the product but the regio and the stereochemistry of the reaction. So when we're talking about hydroboration, we're talking about reacting an organic compound, usually an alkene, with something like BH3, although there are other things we could react the alkene with as well. Now we know that the BH3 is going to react with that alkene. And before we look at what the BH3 does with this double bond, we can look at a three-dimensional model of our alkene reactant. So this is our model. You can see the five-membered ring, the alkene portion with a double bond, the methyl group coming off of it, and you can see that the two carbons in the alkene double bond are sp2 hybridized. They are planar. Now, as the BH3 reacts with our alkene, we can think about it lining up with that double bond. And there are two possible orientations for this boron. It can line up with the less substituted carbon, and the hydrogen's lined up with the more substituted, like I've shown here, or it could do it the other way with the boron and the hydrogen reversed. It turns out that the boron does line up with the less substituted carbon, and there are two reasons for this. We'll talk about the electronic one in a minute, but there's also a steric reason. The boron takes the BH2 portion of the molecule, takes up a little bit more space than the hydrogen, and the CH3 is a little bit more sterically crowded. That's a little bit hard to see in this two-dimensional model. We can look at the three-dimensional model of this. And in this model you can see that the boron, I've got color green and the hydrogen on it there, is lined up underneath my alkene, and if I rotate this, you can see that the methyl group here takes up more space than the hydrogen here, and I've color-coded my substituents on my alkene red in both pictures so that we can keep track of them. So the methyl group takes up more space than this hydrogen, so it's better to have the smaller hydrogen here on the side of the more crowded methyl group. Now, I've drawn my arrows showing how my electrons move. So the electrons move from the double bond to the boron, and from this boron-hydrogen single bond to this carbon. And this is a concerted reaction. All of this happens simultaneously. And we can look at the transition state of this reaction, where the boron is starting to form a bond with this carbon. This hydrogen is starting to form a bond with this carbon. This double bond is starting to break and transition to a single bond. This bond is starting to break. Now, this doesn't all happen perfectly symmetrically. So there's some positive charge that builds up in the carbon and some negative charge that builds up in the boron. The more substituted carbon is better able to bear that partial positive charge than the less substituted carbon. So the partial positive builds up on this carbon and partial negative on the boron. This is another reason why, in addition to the steric reason, that the boron adds to this carbon and the hydrogen adds to this carbon. The partial positive that builds up is better to build up on the more substituted than the less substituted carbon. We can look at this transition state in three dimensions, which is shown here. And you can see the partial bond starting to form, partial bond starting to form, this bond starting to break, this one of the two bonds starting to break here. The important thing, the really important thing about this transition state is you'll notice that the boron and the hydrogen come in from the same face of the double bond. Because they come in from the same face of the double bond, in the product, this boron that gets added and this hydrogen will be on the same side. Another way to look at it is if this boron comes in and this hydrogen comes in from the same side, both this hydrogen and this methyl group, as the product starts to form, start moving upwards. So this hydrogen starts going up, this methyl group starts going up, hydrogen and boron start coming in and form their new bonds. This means a lot for the stereochemistry of the product. It means that this boron and this hydrogen are on the same face and this methyl is on the opposite face of the boron, which we can see here. The boron's going down, methyl group going up, the original hydrogen going up. The hydrogen added to the molecule is going in the same direction as the boron group that it came from. We can look at the product over here. with the hydrogen and the boron on one face and the CH3 and the original hydrogen on the other face. Now you know that we normally don't stop with the borohydrated compound, or we normally react that with something like sodium hydroxide and H2O2 to convert the boron group to an OH group. And we're not going to worry about the stereochemistry of that reaction right now, but the OH does keep the same relative stereochemistry as the boron is replacing.